Hello students, welcome back. We have one more example to go in section 6. It's this example right here, and it can be argued that this is a bit too advanced, or maybe not. I'm not so sure at this moment, so I'm kind of torn between whether to cover this as a regular topic or an optional topic. I'll get a little bit better idea, a little bit clearer idea by the time we actually cover this in the fall. For now, let's just begin. Given pair of positive integers a and b, we must prove the remainder of 2 to the a power minus 1 divided by 2 to the b power minus 1 is 2 to the r power minus 1. You see, the remainder must follow the same structure, where r is the remainder of a divided by b. You see? Let's assume we know everything about the lower cases. A is the divisor, A is a dividend, so it's some quotient times the divisor plus the remainder. Alright, A is QB plus R form, and then the remainder must always follow this inequality, greater than or equal to 0 and strictly less than the divisor. Alright, let's suppose we know everything about the lower cases. And let's define capitals using a to the something power minus 1 structure. Why is this so special? Well, let's relate this to some fancy theory in prime number theory actually, but at this moment the connection is a little bit hard to see. Under these assumptions, the remainder also follows the same format. That's what we have to prove. So capital A is some quotient times capital B plus capital R, and capital R is the remainder, so it must follow this inequality, greater than or equal to 0, but strictly less than the divisor capital B. So we assume this and that as definition, and then for lower cases we assume we know everything. Then the remainder of the capitals must follow the same structure. So if I let capital R as 2 to the r power minus 1, then we must prove that this is a remainder. In other words, it must satisfy this equality and then this inequality. So these two are the things we have to prove. Number 1, equality. Number 2, inequality. That's the structure of the problem. Now, before starting this proof, do you see the apparent beauty of it? 2 to the something power minus 1 is being preserved over. What's so special about that? It applies to the dividend, the divisor, and also the remainder. But not the quotient. Quotient is different. And in the second half, it all applies to the GCD as well. So same structure goes on, except for quotient. It's amazing. That's why I mentioned this as the beautiful theorem or beautiful result. Do you see the beauty of it? I hope you do. Okay, let's go ahead and prove it. And the proof follows the division algorithm. We have to prove these two, this equality and this inequality, right? We are assuming capital R is 2 to the r power minus 1. Then it is indeed a remainder, so it has to follow this equality and this inequality. Which one shall we prove first? Let's prove the inequality first. It's a bit easier. And how do you prove the inequality? Well, obviously, it is related to this inequality here, so that's where we start. Small r is greater than or equal to 0, and strictly less than small b. That's where we start. And then let's apply this 2 to the something power minus 1. So r is less than b. So we take 2 to the r power, then that's less than 2 to the b power, right? Subtracting 1 applies the same way to left-hand side and right-hand side. So we have the desired inequality. 2 to the r power minus 1 is strictly less than 2 to the b power minus 1. How about the first inequality? Well, r is greater than or equal to 0, so 2 to the r power is going to be 2 to the 0 power, first power, second power, third power, and so on. Those are 1, 2, 4, 8, 16, and so on. They're all greater than or equal to 1. So we have this inequality as well. So that proves the desired inequality. Capital R defined this way indeed follows this inequality, greater than or equal to 0, but strictly less than capital B. Now, if we prove this equality as well, then we are going to be done. We wanted to prove that capital R defined this way is indeed the remainder for this operation, capital A divided by capital B. And we proved the inequality. Okay, one more to go. Let's prove the equality. And obviously, we'll have to start from this equality with lower cases. That much is crystal clear, I hope. We use the inequality to get this inequality. So not surprisingly, we'll have to use this equality. By the way, this applies for the special case when A is less than B as well. If I select Q equal to 0, even though that's rare, most of the time we divide big number by smaller number, but it's okay to do it the other way around. All right, ready for some manipulation. Remember, we have to prove this. So 2 to the capital A power, capital A is 2 to the small a power minus 1. That's where we start. All right, 2 to the small a power minus 1. That's where we start. And then that's 2 to the QB plus R. See that? Maybe I'll be bigger font will help. A is QB plus R, so the power, QB plus R power minus 1. Does it make sense? So Q, B is green, and R is red. Yeah, and somehow you have to manipulate so that it is the division algorithm, capital Q times capital B plus R. So that's our aim. How do we fill up this dot dot dot? If we do, that's the end of the proof. All right, a brief recap. This is where we start. And then that applies to the power of 2. And then minus 1. And then somehow you have to prove that this is some quotient times b plus capital R, where b is, 2 to the b power minus 1. Capital R is 2 to the r power minus 1. Okay, how do you do that? Well, here's some basic idea. I want capital R, which is 2 to the r power minus 1. We have minus 1 here. So we want to insert 2 to the r power one way or the other. And this is how you do it. Put it in and subtract so that the net is 0. No change. I just subtracted and added the same thing, so I added 0, so no change. But this is capital R, which we want, and this one here should be capital Q times capital B somehow. All right? All good? Now this is capital R, no problem. I'm going to take these together as a parenthesis. Somehow I have to work this one out. Any good idea? Looks like it can be factored out. 2 to the R power can be factored out. You have 2 to the R power and plus R power. So factor 2 to the R power, and this is what we get. And then, do you get some idea what to do? Probably not, so I'll just give you this. 2 to the QB power, you can rewrite it as 2 to the B power to the Q power, and then 1 as 1 to the Q power. Consequently, what do you get? X to the Q power minus Y to the Q power form, and that can be factored. Alright, this one here is capital R, no problem. It's all set. And the rest here, factoring 2 to the R power out first, and then what's left is actually Q power minus Q power form. So going from here to there is a bit weird, but it works. Once you get that, you can factor it out. To the B power minus 1, and then the cyclotomic term here. So we have this capital R right here, and then 2 to the B power minus 1, B right here, and then the rest is, well, what can I say? They are just a bunch of integers multiplied and added, so it's got an integer. So that becomes Q. So Q times the divisor plus the remainder. We get the desired form. Aside from the power part, we don't really need bigger font. It's easier to read it this way. So we got this capital A's, capital Q times capital B plus capital R, precisely the way we want it. So that completes the proof. Capital R given by the same structure is indeed the remainder. So this 2 to the something power minus 1, if we study those kind of integers, then in the division algorithm, the same structure is preserved over to dividend, divisor, and remainder. Not the quotient, but those three, yes. Moreover, through the Euclidean algorithm, it can be passed over to the GCD as well. So, capital A is 2 to the A power minus 1 as before, capital B is 2 to the B power minus 1 as before, and we define GCD of those capital as capital D. Then the GCD for this capital and GCD for this original small are related, guess what? Exactly the same way. 2 to the D power minus 1. Do you appreciate this beauty? Same structure is being preserved over in the division algorithm and also in the Euclidean algorithm. Before the proof, let me mention one more thing. As an immediate corollary, these two are relatively prime if and only if A and B are relatively prime. So we get this is 1 means 2 to the 1 power minus 1 and vice versa. Okay, let's prove it, and the proof follows Euclidean algorithm. So we have this kind of Euclidean algorithm computation. R0 is A, R1 is B, and then repeated application of the division algorithm of 2RK. And remember, exactly the same structure, 2 to the something power minus 1, is repeated over precisely the same all the way to the end as to the GCD. Therefore, comparing those, we get the desired conclusion. The same structure is preserved over to GCD as well. This thing has a lot to do with prime number theory, but that's getting a bit too advanced. So let's stop here.